Welcome to the Foundry by Forge College. Let's get right into it because we have a truly essential explainer lined up for you today. If you're with us for the Network Configuration Fundamentals lesson, you know we covered the abstract theory behind network topologies and node configuration. But hey, theory is really only half the battle, right? Today, we're taking those blueprints and translating them into applied, production-like test beds. We are going to learn exactly how to configure a mainnet-like environment. So grab your hard hats because we are moving from the safe, perfect, theoretical world into the messy, chaotic, real-world application of Solana deployment. Okay, so you might be wondering, why go through the trouble of building a network simulator in the first place? Well, think of it like a flight simulator. You would absolutely never try to learn how to fly a supersonic jet in a perfectly calm, zero-gravity vacuum. It just wouldn't prepare you for the real world. In the exact same way, your decentralized application, your DApp, simply won't survive the turbulence of mainnet if you only ever test it on a flawless, zero-latency local devnet. I mean, a perfect local environment is comfortable, sure, but it hides the exact types of friction that will eventually bring your application to its knees in production. Here is our blueprint for today. 1. Welcome to the turbulence. 2. 4 pillars of parity. 3. Mapping production measurements. 4. Setting up the validator. 5. Tuning your client behavior. And 6. Validating the test environment. Let's jump in. Section 1. Welcome to the turbulence and escaping the local DevNet illusion. Because testing a ship in a bathtub and just hoping it survives a hurricane is a pretty terrible engineering strategy. Section 2. The 4 pillars of parity. The foundation of our simulation. To actually simulate that hurricane accurately, we need to adjust 4 specific dials. Number 1 is endpoints and routing. This basically means emulating how your RPC requests travel, so adding proxies to simulate distance and load balancers. Number 2 is client behavior. How does your software actually react when a request just hangs? Number 3 is node resources. This means intentionally throttling CPU and I/O so your local node sweats exactly like a production node would. And finally, number 4, observability. You absolutely need the exact same metrics locally as you have in production. Mastering these 4 pillars is exactly the kind of rigorous, advanced learning we emphasize in our programs at Forge College. It's quite literally what separates novice builders from battle-hardened engineers. Section 3. Mapping production measurements to translate real-world data. We need hard data to tune those dials. Let's say in production, your median latency is 80 milliseconds. For your test target, you don't just set a hard, perfect 80 millisecond delay. Instead, you configure your proxy to deliver anywhere from 80 to 120 milliseconds, with random jitter sprinkled in. Why? Because the real world isn't perfectly consistent. And think about your transient error rate. Say it's 0.8% in production. You absolutely must configure your testbed to randomly drop or reject about 0.5% to 1.5% of connections. By explicitly injecting this error rate, you force your testbed to drop connections just like a real load balancer under heavy stress, which really proves whether your app's retry logic actually works. Now, I really want you to focus on this number, 450 milliseconds. This represents the 95th percentile latency from our production baseline. It basically means that while most of your requests take 80 milliseconds, 5% of them are dragging out to almost half a second. And you know, in Web3, a half-second delay feels like a lifetime. This tail latency is the exact turbulence that causes really frustrating cascading failures in production. If your local simulator doesn't artificially hold 5% of its responses for 450 milliseconds, you are going to completely miss the exact bugs that will crash your app on mainnet. Section 4. Setting up the validator, or as I like to call it, building the engine. Think about starting up your local validator. We aren't just running a standard vanilla Solana test validator command. We are pointing the ledger to a persistent directory so cold cache performance actually matters. But more importantly, we need to add a few specific flags, -limit ledger size and -accounts-db skip shrink. By default, local devnets will aggressively prune their data to save your laptop's hard drive space. Mainnet nodes do not have that luxury. They are managing massive, incredibly heavy databases. By using these exact flags, we intentionally avoid aggressive pruning. We are perfectly approximating the heavy, laborious disk activity of a production validator. Seriously, get ready to hear your laptop fan spin up like a jet engine. Section 5. Tuning your client behavior to handle the turbulence. Okay, so now that our local network is hostile and bumpy, we have to actually adjust our client software so it doesn't completely crash. We need to set a generous initial timeout parameter, specifically a 60,000 millisecond timeout for transaction confirmation. Yep, that's a full minute. Why set it so high? Well, giving the client a generous bound prevents those slow 450 millisecond tail latency confirmations we talked about earlier from registering as immediate catastrophic failures. You just have to give the network time to be slow. But what happens when a request actually does fail? You need an explicit retry loop. The crucial part here is implementing 3 core mechanics. First, you set maximum retry attempts, let's say 5 tries. Second, you use exponential backoff. This means you wait 2 seconds, then 4 seconds, then 8 seconds between tries. And third, you add random jitter to that wait time. If you don't cap your attempts and add that jitter, a simple dropped connection can cause an infinite retry loop. And let me tell you, in a production environment, 1,000 users infinitely retrying at the exact same millisecond is what we call an unintentional DDoS attack. You will literally overwhelm your own system. Section 6. Validating the test environment. Time to check the dials. Once your simulator is built, you can't just cross your fingers and assume it works. You have to keep this core principle in mind as you run synthetic probes. Emulate observable behavior, not hidden internals. It is incredibly expensive and honestly frustrating to try and perfectly mirror the exact physical hardware of a production validator on your local machine. It is so much smarter to just use simple software throttling and network proxies to reproduce the latency distributions. If the observable delay is exactly the same, your client software doesn't care if it was caused by a lightweight proxy script or a massive $1 million server rack. So to validate all this, you collect a 24-hour sample of RPC timings from your newly configured testbed, and you put it right next to your production baseline distributions. Just look at them side by side. If your testbed has a 0% error rate, but production has 0.8%, well, you need to go tweak your proxy. You just keep iterating on your proxies and your timeouts until the distributions align perfectly. When they match, that's when you know you have successfully captured lightning in a bottle. And that brings us to the end of today's blueprint. In our next explainer, we are going to take everything we just discussed and apply it in a hands-on lesson, focusing heavily on configuration and resource scripting. We're going to automate these setups so you can spin up a chaotic, realistic network with a single command. I highly encourage you to visit our community at forge.college to continue learning, dive into our courses, and explore a ton of other advanced Web3 resources we have available for you. I want to leave you with one final provocative thought. Think about the code you wrote this week. If your dApp only works in a perfect environment with 0 latency, 0 dropped packets, and infinite resources, does it really work at all? I'm your host from the Foundry, challenging you to stop building for perfect conditions and start engineering for the turbulence. This explainer was made by Forge College. Happy building, and I will see you in the next one.